Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Adjust your pillow, let your body settle into whatever surface is supporting you right now. There's nowhere else you need to be. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cozy corner where the day has finally released its hold? Wherever you are, you're welcome here. Tonight we're going to explore something extraordinary that happened when humanity pointed the most sophisticated telescope ever built toward the oldest light in the universe. The James Webb Space Telescope looked back 13.5 billion years, to a time just 300 million years after the Big Bang itself. What it saw there has puzzled scientists, challenged our understanding and revealed galaxies that, according to everything we thought we knew, shouldn't exist. We'll discover what these impossible galaxies look like, understand why they're so surprising, and contemplate what they might mean for our story of how the universe came to be. But don't worry. This isn't going to be an alarming revelation that undermines everything. Instead, we'll move slowly and carefully through one of the most beautiful mysteries science has encountered in decades, taking our time with each discovery, each image, each question. By the end, I think you'll find not confusion, but wonder. Not anxiety about what we don't know, but peace in the reminder that the universe still has secrets to share, and that we're living in the moment when those secrets are being gently revealed. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for returning to these quiet journeys through space and time. So settle in, let your shoulders drop away from your ears, take a slow breath, and let it out even more slowly. And let's begin our slow drift through the story of what James Webb saw at the edge of time. There's nothing you need to do right now. Just listen and let the story unfold like starlight reaching us from impossibly far away. Let's begin with something that might seem impossible on its own. The idea that we can look backward through time simply by looking outward into space. Light travels fast, extraordinarily fast, but it doesn't travel instantaneously. It moves at roughly 300,000 kilometers per second, which sounds immediate until you consider the distances involved in space. When you look at the moon, you're seeing it as it was about 1.25 seconds ago, because that's how long the light took to travel from the lunar surface to your eyes. When you look at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. The light from our nearest star beyond the sun, Proxima Centauri, takes just over 4 years to reach us, and this connects to something equally important. The farther away something is, the further back in time we're seeing it. When we look at the Andromeda Galaxy, visible to the naked eye on a dark night as a smudge of light, we're seeing it as it was 2.5 million years ago. The light that enters your eye tonight left that galaxy when our ancestors were just beginning to walk upright on the African plains, which helps explain why telescopes are, in a very real sense, time machines. They don't move through time, but they allow us to see through time by gathering light that has been travelling through space for billions of years. The most distant galaxies we can observe are sending us light that began its journey when the universe itself was young, when the first stars were just beginning to ignite, when everything we know today was compressed into a volume almost unimaginably smaller than it is now. But there's another layer to consider here. The universe isn't just large, it's expanding. It has been expanding since the Big Bang, which means that distant galaxies aren't just far away in space, they're also moving away from us. And the farther away they are, the faster they're receding. This expansion stretches the light as it travels, shifting it toward the red end of the spectrum, a phenomenon called redshift. The most distant galaxies are so redshifted that their visible light gets stretched all the way into the infrared portion of the spectrum, invisible to human eyes and to most telescopes. This is where the James Webb Space Telescope becomes essential to our story. Webb was designed specifically to see an infrared light, to capture the stretched and redshifted light from the universe's earliest galaxies. Where the Hubble Space Telescope could peer back perhaps 12 or 13 billion years with difficulty, Webb can look comfortably to 13.5 billion years ago, to just 300 million years after the Big Bang. It can see further back than any telescope before it, gathering light that left its source when the universe was barely 2% of its current age. And this brings us to something equally remarkable: what Webb saw when it finally turned its golden mirrors toward that ancient light. The images came back sharper and clearer than anyone expected, showing not the faint fuzzy smudges scientists anticipated, but galaxies. Distinct, structured, surprisingly mature galaxies glowing in the cosmic dawn. Galaxies that looked, in many ways, like they had no business existing yet. Galaxies that, according to our models of how galaxies form and grow, shouldn't have had time to assemble themselves into the shapes Webb revealed. To understand what Webb found, we need to understand what Webb is and why it took so long to build. The James Webb Space Telescope isn't an upgrade to Hubble, though people often describe it that way. It's something different, built for a different purpose. Where Hubble sees primarily in visible and ultraviolet light, the light your eyes can see, Webb sees in infrared. It detects heat rather than visible light, which makes it perfect for observing the most distant, most red-shifted objects in the universe. Its primary mirror is made of 18 hexagonal segments, covered in a microscopically thin layer of gold, which reflects infrared light beautifully. When fully deployed, those 18 segments work together as a single mirror 6.5 meters across, nearly 3 times the diameter of Hubble's mirror and with about 6 times the light gathering area. But building Webb was extraordinarily difficult. The telescope had to be folded up to fit inside a rocket, then unfold itself in space through a sequence of deployments so complex that engineers called it 30 days of terror. The sunshield alone, a 5-layer structure the size of a tennis court, had to unfold perfectly despite being thinner than a human hair in places. One mistake, one torn membrane or stuck cable, and the entire mission would have failed. And unlike Hubble, which orbits close enough to Earth that astronauts could visit it for repairs, Webb orbits at a point called L2, about 1.5 million kilometers from Earth. If something went wrong, there would be no fixing it. Consider this. The project took nearly 30 years from concept to launch, with costs approaching $10 billion. It was delayed repeatedly, criticised frequently, and at several points nearly cancelled. Scientists who proposed observations for Webb often wondered if they would retire before the telescope launched. Some did. The entire astronomical community held its breath during those 30 days of deployment, knowing that decades of work and hope rested on thousands of mechanisms all working perfectly in the freezing vacuum of space. And this connects to something I find deeply moving about the scientific endeavour. The people who built Webb knew they might never see it work. The engineers who designed components in the early 1990s understood they were building something for the astronomers of the 2020s. They were constructing a gift for the future, working with care and precision on mechanisms they would never personally test in space, trusting that everything would work when the moment finally came. The telescope reached its destination on January 24th, 2022. It spent the next 6 months cooling down, aligning its mirrors, and calibrating its instruments. The mirrors had to be adjusted to within wavelengths of light, positioned so precisely that the entire mirror acts as one perfect surface, despite being made of 18 separate segments. The temperature had to drop to about 40 degrees above absolute zero, cold enough that the telescope's own heat wouldn't swamp the faint infrared signals from distant galaxies. And then, in July of 2022, NASA released the first images. Scientists and the public alike gathered to see what Webb had captured. The first deep field image showed thousands of galaxies in a tiny patch of sky, each one a distant island of stars, many of them appearing as they were billions of years ago. It was immediately clear that Webb could see further and more clearly than any telescope before it. The universe revealed itself in unprecedented detail, layer after layer of cosmic history compressed into a single image. But it was what came next, as scientists began analysing those images and taking new ones, that started to reveal the mystery at the heart of our story tonight. Because Webb didn't just see distant galaxies, it saw galaxies that didn't match our expectations, galaxies that were too large, too bright, too structured for their age. Galaxies that made scientists pause and reconsider theories they'd held for decades. Before we can understand what Webb found that's so surprising, we need to understand what the early universe was supposed to be like. In the beginning, for the first 380,000 years after the Big Bang, the universe was opaque. It was a hot, dense fog of matter and energy, so hot that atoms couldn't hold together. Electrons zipped around freely, scattering light in every direction. You couldn't have seen anything during this time, even if you somehow existed to look, because light couldn't travel in straight lines. It was like trying to see through a thick cloud. Except the cloud was the entire universe. But then something beautiful happened. The universe expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. This process, called recombination, made the universe transparent for the first time. Light could suddenly travel freely through space. The cosmic microwave background, that faint afterglow we can still detect today, is light from this moment. Stretched by billions of years of cosmic expansion from visible light into microwaves. It's the oldest light we can see, a baby picture of the universe taken when it was just 380,000 years old. And this connects to the period scientists call the Cosmic Dark Age. After recombination, the universe was filled with neutral hydrogen gas, but there were no stars yet, no galaxies. It was dark not because it was opaque like before, but because there was nothing producing light. Just vast clouds of hydrogen and helium, the only elements created in the Big Bang, drifting through expanding space. Gravity was pulling these clouds together, slowly, patiently, gathering matter into denser regions. But this process takes time. According to our models, the first stars didn't ignite until perhaps 100 to 200 million years after the Big Bang. These first stars were different from stars today. They formed from pure hydrogen and helium, no heavier elements yet, which meant they could grow extremely massive, perhaps hundreds of times the mass of our Sun. They burned hot and bright and died young, exploding as supernovae and seeding the universe with the first heavy elements. Carbon, oxygen, iron. All the elements that would eventually make planets and people possible. But there's more to this story. The first galaxies would have formed from collections of these early stars, gravity binding them together into larger structures. But this process should have been gradual. Small galaxies would form first, then merge together over hundreds of millions of years to create larger ones. It's a hierarchical process, bottom up, like building a pyramid by starting with small blocks and slowly adding more. Our theories suggested that at just 300 million years after the Big Bang, when the universe was barely past its cosmic dawn, galaxies should be small, irregular, and relatively dim. They might be forming stars vigorously, yes, but they shouldn't have had time to grow very large or to develop organised structures like spiral arms or central bulges. They should be messy, chaotic, still in the process of assembling themselves from the scattered remains of the Dark Age. This expectation wasn't just speculation. It was based on decades of observation, computer simulations, and our understanding of how gravity works. Scientists had used powerful computers to simulate the evolution of the universe from the Big Bang forward, watching as virtual galaxies formed and grew. These simulations consistently showed that large mature galaxies take time to develop. You can't rush the process. There's simply not enough time in the early universe for matter to collapse, stars to form, and galaxies to assemble into the structured systems we see in the universe today. And so, when the James Webb Space Telescope turned its infrared eyes toward the cosmic dawn, scientists expected to see exactly that. Small, irregular proto-galaxies fuzzy clumps of young stars still in the process of becoming something larger. What they saw instead would challenge these expectations in ways both exciting and deeply puzzling. The first hints of something unexpected came quickly after Webb's observations began. Scientists had identified their targets carefully, using Hubble data and theoretical predictions to find the most promising candidates for extremely distant galaxies. They pointed Webb at these regions and waited for the images to arrive. When they did, the galaxies appeared as tiny red dots, their light stretched by cosmic expansion into the infrared wavelengths Webb was designed to detect. But what surprised everyone was how bright some of these dots were. These weren't the faint smudges scientists expected. Some were luminous, surprisingly so, suggesting they contained far more stars than should have been possible given their age. When scientists measured the redshift of these galaxies, determining precisely how far away and therefore how old they were, the numbers were startling. Some appeared to be from just 300 to 500 million years after the Big Bang, in the cosmic dawn. The period we were just discussing. And this connects to something equally important. When scientists analysed the light from these galaxies in detail, looking at its spectrum, they could determine not just how far away the galaxies were, but also how much mass they contained. The brightness and colour of the light told them how many stars were shining, how old those stars were, and how much stellar mass had accumulated. For some galaxies, the numbers were stunning. They seemed to contain tens of billions of stars worth of mass, comparable to our own Milky Way galaxy, but existed at a time when the universe was barely 2% of its current age. Let's pause here and consider what this means. Our Milky Way is a mature galaxy, about 13.6 billion years old, with perhaps 200 to 400 billion stars. It has a structured disk, spiral arms, a central bulge, and a history spanning almost the entire age of the universe. It's had time to grow, to swallow smaller galaxies, to form generation after generation of stars. But some of Webb's discoveries appear to show galaxies with comparable mass existing when the universe was just a few 100 million years old. It was like finding a full-grown oak tree in a forest that had only just been planted. Not impossible, perhaps, but deeply puzzling given everything we understand about how oak trees grow. And just as finding that tree would make a botanist reconsider their understanding of tree growth, finding these massive galaxies made astronomers reconsider their understanding of galaxy formation. The scientific community responded with both excitement and caution. Papers began appearing with titles that asked questions rather than making statements. Extremely massive galaxies at cosmic dawn. A population of red candidate massive galaxies at high redshift. The question marks were important. Scientists were careful not to claim too much too quickly. They knew that extraordinary claims require extraordinary evidence, and they wanted to be sure they weren't being fooled by their data, because there were reasons to be cautious. Measuring the distance and mass of extremely distant galaxies is difficult. The light is faint, stretched across the infrared spectrum in ways that can be misinterpreted. It's possible that some of these galaxies weren't as distant as they appeared, that contamination from foreground objects or unusual dust properties made them look redder and more distant than they actually were. It's possible that the mass estimates were wrong, that these galaxies contained fewer stars than the simple analysis suggested. But as more observations came in, as more candidates were found and analysed, a pattern emerged. These massive luminous galaxies at cosmic dawn weren't flukes or measurement errors. They appeared to be real. There genuinely seemed to be a population of surprisingly large galaxies in the early universe, more than our models predicted should exist. And this discovery, if confirmed and understood, would require us to rethink some fundamental aspects of how galaxies form and grow in the first billion years after the Big Bang. To understand why Webb's discoveries are so surprising, we need to understand the models scientists had built for how galaxies form. These models are based on our understanding of gravity, dark matter, gas dynamics, and star formation. They're sophisticated computer simulations that start with the conditions of the early universe, the tiny density fluctuations we see in the cosmic microwave background, and evolve those fluctuations forward in time according to physical laws we've measured and tested. They're run on some of the most powerful supercomputers in the world, tracking billions of particles representing dark matter, gas, and stars as they interact over billions of years of cosmic time. And these models have been remarkably successful. They explain the large-scale structure of the universe, the distribution of galaxies into clusters and filaments separated by vast voids. They explain how galaxies grow through mergers, how dark matter halos provide the gravitational scaffolding for visible matter to accumulate, how supermassive black holes form at galaxy centers and influence their host galaxies through feedback. They match observations of galaxies at many different cosmic epochs, from the universe at half its current age all the way up to the present day. But there's something these models predicted about the early universe. Galaxies should be smaller back then. This isn't an arbitrary assumption, it's a consequence of how hierarchical structure formation works. In the standard model, small dark matter halos form first, then merge to form larger halos over time. Galaxies form within these halos, growing as their host halos grow. The process is gradual, cumulative. The biggest galaxies in the universe today got that way by consuming smaller galaxies over billions of years. According to these models, at 300 to 500 million years after the Big Bang, the universe simply hadn't had enough time for many large dark matter halos to form, which meant there wasn't enough gravitational potential to gather the massive amounts of gas needed to form the most massive galaxies. Star formation should be vigorous, yes, but the total mass assembled into any single galaxy should be limited by how much dark matter had collapsed into bound structures by that time. And this connects to something called the baryon budget, a fundamental constraint on how much normal matter, the stuff stars are made from, can exist in any given region. Baryons are particles like protons and neutrons, the components of atoms, as opposed to dark matter which doesn't interact with light and makes up about 85% of the matter in the universe. The cosmic ratio of baryons to dark matter is fixed by conditions in the Big Bang, about 1 baryon for every 5.5 dark matter particles by mass. You can't cheat this ratio. A dark matter halo of a certain mass can only gather a certain amount of baryonic matter. In the early universe, according to the models, even the most massive dark matter halos that had collapsed by 300 million years after the Big Bang shouldn't have been massive enough to gather the amount of baryonic matter needed to form galaxies with tens of billions of solar masses worth of stars. Not impossible, but highly improbable. The models allowed for some scatter, some galaxies forming more efficiently than others, but they didn't predict a substantial population of such massive galaxies so early. Yet Webb seemed to be finding exactly that. Multiple candidates for very massive galaxies at cosmic dawn, galaxies that appeared to contain more stars than they should have been able to form given the time and resources available. If these observations hold up, if they're confirmed with additional data and scrutiny, then something about our models needs to change. Either galaxies can form more efficiently in the early universe than we thought, converting gas into stars more quickly, or the hierarchical assembly process happened faster than simulation suggests. Or there's some other mechanism we haven't fully appreciated that allows for earlier formation of massive structures. This is what makes the discovery so profound. It's not that galaxies existing in the early universe is surprising. We expected early galaxies. It's that they seem too mature, too massive, too organized for their age. And understanding why, resolving this tension between observation and theory, will require careful work, more data, and perhaps new physics, or at least new insights into how the physics we know operates under extreme conditions. Let that thought settle as we move forward into the deeper details of what Webb has shown us, and what scientists are now trying to understand. Let's look more carefully at what these early galaxies actually look like in Webb's images. They appear as tiny red dots, sometimes barely larger than a single pixel, scattered among thousands of other galaxies in the deep field images Webb captures. The redness is the key. It's not that the galaxies are actually red in any intrinsic sense. It's that their light has been stretched by cosmic expansion during its billions of years' journey to us. Light that left these galaxies as blue or ultraviolet, the light from hot young stars, arrives at Webb's detectors as infrared, light with wavelengths longer than human eyes can see. The more redshifted the galaxy, the older and more distant it is, and Webb's filters can measure this redshift with remarkable precision. Some of these galaxies are what astronomers call dropout candidates. They're detected strongly in redder filters, but invisible or very faint in bluer ones. This dropout pattern is a signature of extremely high redshift. It means the galaxy's light has been stretched so much that even the far ultraviolet light it originally emitted is now shifted into the infrared. And when scientists measure the precise dropout pattern and model it carefully, they can estimate the redshift, the distance, and therefore the cosmic epoch when the light was emitted. But what's striking about some of Webb's discoveries is not just that they're distant, but that they're bright for their distance. A galaxy's apparent brightness depends on two things: its intrinsic luminosity, how much light it's actually producing, and its distance, how far that light has to travel to reach us. Very distant galaxies should generally appear faint simply because they're so far away. Yet some of Webb's candidates shine surprisingly brightly, suggesting they're producing enormous amounts of light, which in turn suggests they contain many stars. And this connects to something equally important about how we measure galaxy masses. Astronomers can't count individual stars in these distant galaxies. They're too far away, too faint. Instead, scientists measure the total light and analyze its spectrum, the way the light is distributed across different wavelengths. The spectrum tells a story. Hot blue stars produce more light at shorter wavelengths. Cooler red stars produce more at longer wavelengths. Old stellar populations, where massive blue stars have already died and only longer-lived red stars remain, have different spectral signatures than young populations still forming massive stars. By modelling the spectrum carefully, comparing it to templates of different stellar populations, scientists can estimate the stellar mass, the total mass locked up in stars. It's not a perfect measurement. There are uncertainties, assumptions about the star formation history, the ages of the stars, the amount of dust obscuring the light, but it's the best tool we have for weighing distant galaxies. And when scientists applied this technique to some of Webb's most distant galaxies, the numbers that came back were startling. One galaxy, with the catalogue designation JADES GSZ 130, appeared at a redshift suggesting it existed just 330 million years after the Big Bang. Analysis of its light suggested it contained roughly 1 billion solar masses of stars. Not the most massive galaxy Webb found, but significant for such an early epoch. Another candidate, part of a study examining red massive galaxies, appeared to contain tens of billions of solar masses at a time when the universe was just 500 million years old. These aren't the only examples. Webb has identified multiple candidates for massive galaxies in the cosmic dawn, enough that they appear to represent a real population rather than rare flukes. And this is where the tension with theory becomes acute, because our models predicted maybe one or two such massive galaxies in the volumes of space Webb has observed so far, but Webb seems to be finding many more than that. The abundance, the sheer number of these galaxies is as surprising as their existence. But mass isn't the only surprising feature of these early galaxies. Some of them show signs of maturity that seem inconsistent with their youth. When we look at nearby galaxies in the present-day universe, we see structure. Spiral galaxies have elegant arms winding outward from central bulges. Elliptical galaxies have smooth, rounded profiles. Even irregular galaxies, the more chaotic systems, have regions where star formation is concentrated and other regions that are quieter. This structure develops over time as galaxies interact with their environment, merge with other galaxies, form stars, and settle into equilibrium between various forces. In the early universe, scientists expected galaxies to be less structured, more chaotic. They should be clumpy. Irregular systems where star formation happens in scattered bursts rather than in organised patterns. They should be actively growing, still assembling, not yet settled into the morphologies we see today. And for many early galaxies Webb has observed, this expectation holds true. They do look irregular, clumpy, still very much under construction. But some don't. Some of Webb's most distant galaxies show hints of structure, perhaps a disk-like shape or a concentrated central region. Some appear to have relatively smooth light distributions rather than the expected clumpiness. This doesn't mean they have fully formed spiral arms. The resolution isn't good enough to see such fine details at those distances. But they seem more organised than theory predicted they should be. And this connects to the question of how quickly galaxies can settle into equilibrium. A newly formed galaxy is a chaotic place. Gas is still falling in, stars are forming in bursts, supernova explosions are driving material back out into space. It's a turbulent, dynamic environment. But over time, as the star formation rate stabilises, as the galaxy's gravitational potential deepens, as feedback processes balance infall, the system settles down. It develops a stable structure. In nearby galaxies, this maturation process clearly took billions of years. Yet some of Webb's galaxies, less than 1 billion years old in absolute terms, seem to have progressed further along this maturation pathway than expected. They look, in some sense, old for their age. And this raises fascinating questions about how quickly galaxies can evolve, how rapidly they can transition from chaotic proto-galaxies to more settled systems. There's another aspect to this maturity paradox, the colour of these galaxies. Some of the massive galaxy candidates Webb found are not just bright, they're red, redder than you'd expect for young galaxies. This redness, beyond what cosmic expansion alone would cause, suggests they contain older stellar populations. It suggests they've already formed most of their stars and are now aging, with their massive blue stars having already died and only longer-lived red stars remaining. But this seems to create a temporal impossibility. If a galaxy at 500 million years after the Big Bang contains old red stars, when did those stars form? Stars take time to age. A massive star might live only a few million years, but to build up a population dominated by older stars requires that most of the star formation happened earlier still, perhaps at 300 or 400 million years after the Big Bang. And if that's the case, then the star formation had to have been incredibly rapid and efficient. Converting gas into stars faster than our models suggest is typical. This is the paradox. To explain the properties of some of Webb's galaxies, we need star formation to have started very early and proceeded very efficiently. But our models of the early universe suggest there shouldn't have been enough assembled mass to support such vigorous star formation so quickly. Something doesn't quite fit, and scientists are working to understand what. It's possible the observations are being misinterpreted. Perhaps dust in these galaxies is making them appear redder and therefore older than they actually are. Perhaps the mass estimates are overestimated due to unusual stellar populations or other factors not fully accounted for in the models. These are active areas of investigation, and many of the most surprising candidates are being followed up with more detailed observations to confirm or refute the initial interpretations. But it's also possible that our models need adjustment, that we're learning something new about how efficiently galaxies can form in the early universe, or about how dark matter is distributed on small scales, or about feedback processes that regulate star formation. This is how science progresses. Through the creative tension between theory and observation, each pushing the other toward deeper understanding. There's another mystery woven through Webb's discoveries, one that adds another layer to the story of these impossible galaxies: supermassive black holes. At the centre of most large galaxies, including our own Milky Way, sits a supermassive black hole. an object containing millions or even billions of times the mass of the Sun compressed into a region smaller than our solar system. These black holes play an important role in galaxy evolution. They can power quasars, the most luminous objects in the universe, when they actively consume matter. They can also drive powerful winds that blow gas out of their host galaxies, regulating star formation. We've known for decades that supermassive black holes and their host galaxies grow together. Their properties correlated in ways that suggest they influence each other's development. But how these black holes form in the first place has always been somewhat mysterious. In the present-day universe, we understand that black holes can grow by accreting matter and by merging with other black holes, but you need a seed, an initial black hole to grow from. The most straightforward mechanism is the death of a massive star, which can leave behind a stellar mass black hole of perhaps 10 to 100 solar masses. But growing from 100 solar masses to 1 billion solar masses takes time, even if the black hole is consuming matter as fast as physics allows. And this connects to something Webb has revealed: quasars and active black holes in the early universe. Some at redshifts corresponding to less than 1 billion years after the Big Bang. The black holes powering these quasars must already contain billions of solar masses. Given the time constraints, given how fast black holes can realistically grow, these black holes must have formed very early, perhaps from seeds that were already quite massive, more massive than what stellar death alone would produce. Scientists have proposed various mechanisms for forming these massive seed black holes. Direct collapse of gas into black holes without forming stars first, or mergers of dense star clusters, or other exotic processes. But regardless of the mechanism, the presence of supermassive black holes so early in cosmic history adds to the puzzle of early galaxy formation, because black holes and galaxies appear to grow together. If there are massive black holes early on, there should also be massive galaxies, and vice versa. Some of Webb's most distant galaxies show signatures that might indicate active black holes at their centres. The light from these galaxies has spectral features suggesting very hot gas that might be heated by falling into a black hole rather than by starlight alone. If confirmed, this would mean that not only did massive galaxies form surprisingly early, but massive black holes did too, and the two were already connected in the cosmic dawn. This raises profound questions about the very first generation of objects in the universe. Did the first stars form, live their brief lives, and create stellar mass black holes that then merged and grew? Or did some regions collapse directly into more massive black holes? Did the first galaxies form around these black holes, or did the black holes form within galaxies that were already assembling? The sequence of events, the cause and effect, is still being unravelled. What's becoming clear from Webb's observations is that the early universe was more active, more dynamic, and more mature than we previously thought. The cosmic dawn wasn't a slow, gradual awakening. It was perhaps more like a rapid ignition, with structures forming and evolving on timescales that pushed the boundaries of what our models predict is possible. And this realization, uncomfortable as it might be for theories long held, is also deeply exciting, because it means we're learning something fundamentally new about how the universe came to be the way it is. Before we accept these observations as definitive proof that our theories need major revision, we need to consider the possibility that we're being deceived by what we're seeing. Dust is one of the prime suspects in this deception. Interstellar dust, tiny grains of carbon and silicate minerals floating in space, has a powerful effect on light. It absorbs and scatters shorter wavelengths more efficiently than longer wavelengths, which means it makes objects appear redder than they actually are. This is the same reason sunsets are red. You're looking at the sun through a thicker layer of Earth's atmosphere, which contains particles that scatter blue light away and let red light through. In galaxies, dust forms from the debris of dead stars, the carbon and heavier elements expelled in supernova explosions and stellar winds. In the present-day universe, many galaxies contain substantial amounts of dust, enough to significantly redden and dim their light. But in the very early universe, there shouldn't be much dust yet. The first stars, forming from pure hydrogen and helium, didn't create much dust when they died. It takes multiple generations of stars, each dying and enriching the interstellar medium with heavier elements, to build up significant dust reservoirs. Yet if there is more dust in early galaxies than models predict, it could explain some of Webb's observations. Dust would make galaxies appear redder, which could be misinterpreted as evidence for older stellar populations. Dust could also make galaxies appear to be at higher redshifts than they actually are, if the dust reddening is mistaken for cosmological redshift. This would mean some of Webb's most distant candidates might actually be closer, more typical galaxies that happen to contain unusual amounts of dust. And this connects to the careful work scientists must do to distinguish between different explanations for a galaxy's colour. They need to measure the galaxy's spectrum across many different wavelengths, looking for specific features that can only come from redshift or only from dust. They need to model the dust properties, which can vary depending on the dust composition and temperature. They need to consider whether the dust is distributed smoothly through the galaxy or concentrated in certain regions. All of this requires follow-up observations, often with different instruments, sometimes requiring multiple exposures to gather enough light for detailed spectroscopy. Some of Webb's candidates have received this careful scrutiny. Scientists have measured their spectra and looked for emission lines, narrow spikes of light at specific wavelengths produced by glowing gas. These emission lines act like fingerprints, and their positions can be measured very precisely. When redshifted, they move to longer wavelengths by a factor that depends only on the cosmic expansion, not on dust. By measuring where these lines appear, scientists can determine the true redshift and therefore the true distance to the galaxy. In some cases, this careful spectroscopy has confirmed that galaxies are indeed as distant as the initial photometric estimates suggested. The galaxies really are in the cosmic dawn, really are seeing the universe at just a few 100 million years old. In other cases, follow-up has revealed that some candidates are not as distant as initially thought, that they're more ordinary galaxies at lower redshifts whose light was contaminated or misinterpreted in the initial analysis. This is the normal process of science. The first observations are often based on broadband photometry, measuring light through a few different filters to estimate properties quickly. But confirmation requires spectroscopy, detailed measurements that take more time but provide much more certain answers. As Webb continues its mission, more and more of these candidate galaxies are receiving spectroscopic follow-up, and the picture is gradually becoming clearer. What's emerging is that while some candidates have been ruled out, many remain confirmed as genuinely distant and genuinely massive. The abundance of massive galaxies at cosmic dawn is being refined, with estimates changing as more data comes in, but the basic finding appears robust. There are more massive, mature-looking galaxies in the early universe than our standard models predicted. Not all of them, not every red dot in Webb's images, but enough to constitute a real discrepancy that needs explanation. One way to understand the significance of Webb's findings is to think in terms of abundance. How many massive galaxies exist per unit volume of space at different cosmic epochs? Astronomers conduct what they call cosmic censuses, surveys designed to count how many galaxies of different types and masses exist at different distances. By combining data from multiple surveys, they build up a picture of the galaxy population across cosmic time. They learn how the number of massive galaxies evolves, how the star formation rate changes, how galaxies grow and merge. This statistical picture complements the detailed studies of individual objects, giving us a sense of what's typical and what's rare. Before Webb, the cosmic census of the early universe was based primarily on Hubble observations. Those observations found some early galaxies, including a few candidates for very massive ones. But the numbers were small, and the uncertainties were large. Hubble was pushing its limits to see back to cosmic dawn, detecting only the brightest and most obvious galaxies at those epochs. There was always a sense that we were seeing just the tip of the iceberg. that many early galaxies were too faint or too red for Hubble to detect. Webb changed this. Its infrared sensitivity and large collecting area allow it to see much fainter and much redder galaxies than Hubble could. The cosmic census of the early universe can now be conducted with much greater completeness, and as Webb's data accumulates, as more surveys are completed and analysed, the numbers are becoming more solid. What those numbers are showing is that the abundance of massive galaxies at cosmic dawn is higher than the pre-Webb models predicted. Not vastly higher, not by orders of magnitude, but significantly so. The models predicted that you might find one or two galaxies with masses above 10 billion solar masses in a certain volume of space at redshift 7 or 8, corresponding to the universe at around 500 million years old. Webb is finding several times more than that. And this connects to something called the cosmic star formation history, the rate at which the universe as a whole is converting gas into stars over time. The standard picture, based on decades of observation, showed that the cosmic star formation rate rises from the early universe to a peak at around 10 to 11 billion years ago, when the universe was forming stars most vigorously, then declines toward the present day. This rise and fall makes sense in the context of hierarchical galaxy formation. More gas available in the past means more star formation, but as galaxies exhaust their gas supplies, and as cosmic expansion dilutes the remaining gas, star formation slows. But if there are more massive galaxies forming earlier than expected, it suggests the cosmic star formation history might be different at the earliest times. It suggests that star formation might have ramped up faster than we thought, or that star formation efficiency, the fraction of gas converted into stars, was higher in the early universe than models assumed. This has implications for our understanding of cosmic reionization, the process by which the first stars and galaxies ionize the hydrogen gas filling the universe. Reionization is one of the major phase transitions in cosmic history, transforming the universe from neutral to ionized, from opaque to transparent at certain wavelengths. The timing and sources of reionization are still being studied, but it's clear that star-forming galaxies played a major role. If there were more early galaxies forming more stars than we thought, they would have produced more ionizing radiation, potentially completing reionization earlier or more efficiently. All of this is still being sorted out. The cosmic census with Webb is ongoing, with new surveys being conducted and existing ones being analysed. The numbers are being refined. The uncertainties are being reduced, and the theoretical models are being updated to match the observations. It's a dynamic time in cosmology, a period of adjustment where observations are outpacing theory, and everyone is working to catch up. And as we move forward, let's shift our focus from the numbers and statistics to something perhaps more profound. What these discoveries might mean for our place in the universe, and for our understanding of how common or rare our own existence might be in the cosmic story. Let's take a moment to consider what it means when observations surprise us this profoundly. Science is sometimes portrayed as a collection of facts, a body of knowledge that's fixed and unchanging. But that's not really how science works. Science is better understood as a process, a method for asking questions about the natural world and testing possible answers against evidence. Theories are our best current explanations for how things work, built on decades or even centuries of observation and experiment, refined and improved as new data becomes available. The standard model of cosmology, the framework scientists use to understand the universe's history and structure, is one of humanity's greatest intellectual achievements. It explains an enormous range of phenomena with remarkable precision. The cosmic microwave background and its tiny temperature fluctuations, the abundance of light elements created in the Big Bang, the large-scale structure of galaxies and dark matter, the accelerating expansion driven by dark energy. It has made successful predictions that were later confirmed by observation, like the existence of the CMB itself before it was detected in the 1960s. But no theory is perfect. Every model has its uncertainties, its approximations, its assumptions. The standard cosmological model involves dark matter and dark energy, components we know exist through their gravitational effects, but whose fundamental nature remains mysterious. It involves complex processes like star formation and feedback that operate on small scales, smaller than cosmological simulations can fully resolve, and must therefore be approximated using simplified prescriptions. And this connects to why Webb's observations are both challenging and valuable. They're not overturning everything we know. They're not suggesting the Big Bang didn't happen, or that our basic understanding of cosmic expansion is wrong. Rather, they're revealing that some of the detailed predictions of our models, particularly about the earliest galaxies, might need revision. They're pointing to aspects of galaxy formation that we haven't fully understood, mechanisms that might operate differently in the early universe than in the cosmos today. This is how progress happens in science. Observations that don't quite match predictions are opportunities to learn, to refine our understanding, to discover new physics or new aspects of known physics operating in extreme conditions. The history of cosmology is full of such moments. The discovery that the universe is expanding, the realization that most of the matter is dark, the surprising finding that the expansion is accelerating. Each of these observations initially seemed to contradict prevailing theories, but each ultimately led to deeper understanding. The tension between Webb's observations and theoretical predictions is being addressed in multiple ways. Some scientists are revisiting the computer simulations, adjusting the parameters that control star formation efficiency or feedback strength to see if reasonable modifications can produce more early massive galaxies without breaking the things the models already explain well. Others are exploring whether our understanding of dark matter needs refinement, whether dark matter halos might collapse and merge faster in certain conditions than the standard models assume. Still others are questioning whether all the mass in these early galaxies is really in stars, or whether some might be in very dense gas clouds, or even in massive black holes that contribute to the light in ways that mimic stellar populations. There are also investigations into whether the measurement techniques themselves might have systematic biases, whether there are subtle effects in the dust corrections or spectral modelling that could shift the derived masses and ages in ways that relieve the tension. All of these approaches are being pursued simultaneously, which is how science makes progress when faced with puzzles. Multiple teams working independently, trying different approaches, comparing results, arguing about interpretations. It's a messy, human process, full of false starts and disagreements. But it's also remarkably effective at eventually converging on truth. What's important to understand is that this tension, this discomfort between observation and theory, is not a crisis. It's not a failure of science. It's science working as it should, using increasingly powerful instruments to probe nature more deeply and accepting that nature might surprise us. The goal isn't to force observations to fit theory, but to let observations guide us toward better theories. To truly understand what might be happening with these early galaxies, we need to consider the invisible scaffolding that holds them together. Dark matter. Dark matter is strange stuff. We can't see it. It doesn't emit or absorb light. It doesn't interact with normal matter through any force except gravity. Yet it dominates the matter content of the universe, outweighing normal atoms by about 5 to 1. We know it exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by the gravity of their visible stars alone. Galaxy clusters bend light from background objects more than their visible mass could explain. The cosmic microwave background has patterns that can only be explained if dark matter was clumping together in the early universe. In the standard model of galaxy formation, dark matter provides the gravitational wells within which normal matter accumulates. Dark matter collapses first, because it's not affected by radiation pressure or gas dynamics, and forms halos. These halos then attract normal matter, which falls in, heats up, cools down, and forms stars. The properties of galaxies, their masses and sizes and star formation rates, are fundamentally determined by the properties of their dark matter halos. And this connects to one of the key constraints on early galaxy formation. Dark matter halos grow through gravitational collapse, a process that takes time. According to simulations, the most massive dark matter halos in the early universe, at 300 million years after the Big Bang, should have masses of perhaps a few billion times the Sun, maybe up to 10 billion in the rarest cases. These halos can then gather normal matter up to about 1/6 their total mass, based on the cosmic baryon fraction, which would give you at most a couple billion solar masses of normal matter. And only a fraction of that gets turned into stars. Yet some of Webb's galaxies appear to contain tens of billions of solar masses of stars. If these measurements are correct, they require either that the dark matter halos are more massive than predicted, that the normal matter fraction is higher than the cosmic average, that star formation efficiency is much higher than assumed, or some combination of all three. One possibility being explored is that dark matter might clump more efficiently on small scales than the standard models assume. The nature of dark matter, what particle or field it actually is, remains unknown. The most popular candidate is something called cold dark matter, particles that move slowly compared to the speed of a light and therefore clump readily under gravity. But there are other possibilities: warm dark matter, which moves faster and clumps less efficiently, or self-interacting dark matter, which can collide with itself and transfer energy, or even more exotic options. If dark matter has properties slightly different from the simplest cold dark matter models, it could change how quickly halos form and grow in the early universe. For example, if dark matter self-interactions allow energy to be dissipated, halos could collapse more compactly, potentially gathering more normal matter into their centres where stars can form. Or if dark matter has some small coupling to normal matter beyond just gravity, it could affect how efficiently gas cools and forms stars within halos. These are speculative ideas, and they're constrained by many other observations that the standard cold dark matter model explains well. But Webb's observations are prompting scientists to think more carefully about whether there might be subtle variations in dark matter properties that could resolve the tension without breaking everything else the model achieves. There's another aspect to consider: the role of dark matter in seeding the formation of the first supermassive black holes. Some theories suggest that the densest concentrations of dark matter in the early universe, places where multiple dark matter streams intersected, could have provided unique environments for rapid collapse and black hole formation. If supermassive black hole seeds formed in these special locations, they could have then attracted and helped assemble the massive galaxies around them more quickly than the standard bottom-up scenario would predict. This idea inverts the usual sequence. Instead of galaxies forming first and then developing central black holes as a consequence of their growth, the black holes could form first and catalyse galaxy formation. It's an intriguing possibility that would naturally explain why some early galaxies are both massive and host active black holes. But like all such ideas, it needs to be worked out in detail and tested against the full range of observations, not just Webb's early galaxy candidates. What's becoming clear is that dark matter, this invisible component that makes up most of the universe's mass, plays a more subtle and complex role than we might have appreciated. It's not just passive scaffolding. The details of how it behaves, how it interacts with itself and with normal matter, might be crucial for understanding the very first stages of galaxy formation. Another key variable in the galaxy formation equation is how efficiently gas gets converted into stars, and how stellar and black hole activity feeds back on that process. Star formation is wasteful. When a cloud of interstellar gas collapses under its own gravity, only a small fraction of the gas actually ends up in stars. Much of it is heated or blown away by the energetic processes associated with star formation itself. Stellar winds from massive young stars, supernova explosions when those stars die, radiation pressure from the intense light produced by hot stars. This feedback limits how much of a galaxy's gas reservoir gets turned into stars in any given burst of star formation. In the present-day universe, we observe that the star formation efficiency, the fraction of available gas converted to stars is quite low, typically a few % per million years in a typical galaxy like the Milky Way. This low efficiency is thought to be maintained by feedback. Stars form, produce energy, drive winds that heat or eject gas, temporarily shutting down further star formation until the gas cools and collapses again. It's a self-regulating cycle that prevents galaxies from turning all their gas into stars too quickly. But perhaps in the early universe, things were different. Perhaps feedback was less effective, allowing star formation to be more efficient, or perhaps certain conditions like higher gas densities or different gas compositions promoted more rapid star formation. If early galaxies could convert a higher fraction of their available gas into stars, it would help explain how they became so massive so quickly. And this connects to the role of the first generation of stars, what astronomers call population 3 stars. These stars formed from gas that contained no elements heavier than hydrogen and helium, because heavy elements didn't exist yet. Theory suggests they could grow extremely massive, perhaps 100 to several hundred times the mass of the Sun, much larger than the most massive stars forming today. These first stars would have been incredibly luminous and would have died young, exploding as supernovae after just a few million years. The energy released by population 3 supernovae would have been substantial, potentially driving powerful winds that could blow gas out of their host protogalaxies. This feedback could have suppressed further star formation, keeping early galaxies small, but it's also possible that the conditions in dense dark matter halos allowed gas to recollapse quickly after being expelled, or that the first heavy elements produced by population 3 stars actually promoted more efficient star formation by providing coolants that helped gas clouds collapse more readily. These are complex processes that computer simulations try to model, but there are uncertainties in the prescriptions used. The simulations can't resolve individual stars or even individual molecular clouds where stars form. They use simplified rules based on our understanding of physics and calibrated against observations of nearby galaxies. But if those rules don't quite capture what happens in the extreme conditions of the early universe, the simulations might not predict the right galaxy masses and star formation rates at early times. Scientists are now exploring whether reasonable changes to the star formation efficiency or feedback prescriptions can reconcile models with Webb's observations. Some recent simulations that allow for higher star formation efficiency in dense, rapidly collapsing systems have found that they can produce more massive early galaxies without dramatically changing predictions at later times. The key is finding modifications that are physically motivated, that don't simply amount to tuning parameters to fit one set of observations while breaking others. There's also the role of black hole feedback to consider. When supermassive black holes actively accrete matter, they release enormous amounts of energy, sometimes more than the entire stellar light output of their host galaxy. This energy can heat gas throughout the galaxy, driving powerful winds that can temporarily halt star formation. But black hole feedback can also be positive, compressing gas in certain regions and triggering star formation. The net effect depends on many factors: the black hole mass, the accretion rate, how the energy couples to the surrounding gas, the geometry of the system. If massive black holes formed early, and their feedback operated differently than in the present-day universe, it could have influenced early galaxy evolution in ways that aren't fully captured in current models. Understanding this requires combining simulations of galaxy formation with detailed models of black hole growth and feedback, a technically challenging task that many research groups are now pursuing. As scientists work to reconcile observations with theory, a revised picture of the early universe is beginning to emerge, one that's richer and more nuanced than what we had before. The old picture, the one held for the past couple of decades, suggested a relatively slow awakening of the cosmos after the Big Bang. The first stars ignite at maybe 100 million years, forming in small groups within small dark matter halos. These groups merge gradually over hundreds of millions of years to form the first galaxies. Those first galaxies are small and irregular, slowly growing through continued star formation and mergers. By 500 million years after the Big Bang, there are some galaxies, but they're modest in size and mass. Large galaxies like the Milky Way don't form until much later, after billions of years of accumulated growth. The new picture, informed by Webb's observations, suggests that things happened faster and more efficiently than we thought. The first stars might form even earlier, and might rapidly produce the heavy elements needed for efficient subsequent star formation. The first dark matter halos might have assembled mass more quickly, perhaps aided by unique conditions in the early universe that we're still working to understand. Star formation in these early systems might have been more efficient, converting a larger fraction of available gas into stars before feedback effects shut it down. The result is a universe that, by 300 to 500 million years after the Big Bang, already contains a population of relatively massive, relatively mature-looking galaxies. Not in huge numbers, they're still rare compared to later cosmic epochs, but present nonetheless. These galaxies coexist with many smaller, less massive systems, the more typical early galaxies that fit better with our old expectations. But the presence of even a modest number of massive galaxies at such early times tells us that the path from the cosmic dark age to the galaxy-filled universe of today was faster and more varied than we appreciated. And this connects to our understanding of cosmic rionization, that major transition when the universe shifted from neutral to ionized. The timing of rionization is constrained by observations of the cosmic microwave background, and by studies of distant quasars, whose spectra tell us about the ionization state of the gas they shine through. These observations suggest that reionization was largely complete by around 1 billion years after the Big Bang, and well underway by 600 million years. If there were more star-forming galaxies in the early universe than we thought, they would have collectively produced more ultraviolet radiation, the light energetic enough to ionize hydrogen. This could mean that galaxies played an even larger role in reionization than previously estimated, perhaps dominating over other potential sources like accreting black holes. It could also mean that the ionization of the universe proceeded more rapidly once it started, perhaps beginning earlier than some models predicted. The revised cosmic story is still being written. Each new Webb observation, each follow-up study that confirms or refutes early candidates, each updated simulation that tests new ideas, adds a paragraph or a chapter. It will take time for the community to converge on a consensus picture, for the observations to be fully understood and the theories to be appropriately modified. But the broad outline is becoming clearer. The early universe was more active, more dynamic, more capable of producing complex structures than we gave it credit for. This doesn't overturn the Big Bang model or our basic cosmological framework. The universe is still 13.8 billion years old. It's still expanded from a hot, dense state. Dark matter and dark energy still dominate its composition. What's changing is our understanding of the details, the specific processes by which the first galaxies formed and evolved. And that's exactly the kind of refinement that happens as observations improve, as telescopes like Webb give us clearer windows into cosmic history. There's something humbling and exciting about this process. Humbling because it reminds us that despite all our sophistication, despite our powerful computers and elegant equations, nature can still surprise us. Exciting because each surprise is an opportunity to learn, to dig deeper, to ask questions we didn't know to ask before. To fully appreciate Webb's contribution, it's worth reflecting on what Hubble could and couldn't see in the early universe. The Hubble Space Telescope, launched in 1990 and operated for more than 3 decades, is one of the most successful scientific instruments ever built. Its images have become iconic. The pillars of creation, the Hubble Deep Field revealing thousands of galaxies in a tiny patch of sky, the Hubble Ultra Deep Field going even deeper. Hubble transformed our understanding of the universe, measuring the expansion rate, revealing the accelerating expansion that led to the discovery of dark energy, studying galaxies across billions of years of cosmic history. But Hubble had limitations. It was optimized for visible and ultraviolet light, the wavelengths we see with our eyes. It had some infrared capability, particularly after instruments were added or upgraded during servicing missions, but its infrared sensitivity was limited. And for studying the very early universe, infrared is crucial, because that's where the light from the most distant galaxies ends up after being stretched by cosmic expansion. Hubble could detect galaxies at redshift 6, 7, even occasionally 8, corresponding to the universe at less than 1 billion years old. It found some candidates for even higher redshifts, though many of these turned out to be misidentifications or required extraordinary integration times to see at all. But Hubble was pushing its limits at those distances. The galaxies appeared as faint red smudges, often barely distinguishable from noise. Detailed study was difficult or impossible, and this connects to a phenomenon called sample bias. When you can only detect the brightest objects, you get a skewed picture of the population. Hubble's census of the early universe was biased toward the most luminous galaxies, the ones forming stars most vigorously, or hosting the brightest active black holes. The more typical early galaxies, smaller and dimmer, were largely invisible to Hubble. And the reddest galaxies, those with older stellar populations or significant dust content, were especially hard for Hubble to detect, because their light was shifted to wavelengths, where Hubble's sensitivity dropped off. Webb doesn't have these limitations. Its large primary mirror gathers much more light than Hubble's, making faint objects brighter. Its infrared instruments are optimized for precisely the wavelengths where the most distant galaxies shine. It can see galaxies that were completely invisible to Hubble, either because they were too faint, too red, or both. And this completeness, this ability to see a fuller census of the early galaxy population, is what revealed the discrepancy with theoretical predictions. Some of the massive red galaxies Webb found likely existed in regions of sky that Hubble imaged deeply, but Hubble simply couldn't see them. They were hiding in plain sight, too faint or too red for Hubble's instruments to detect above the background noise. Webb's observations didn't discover new regions of the universe. It revealed what was always there but invisible to previous telescopes. This is an important point because it affects how we interpret the surprise. It's not that the universe suddenly became different. It's that our window into the early universe suddenly became much clearer, and we could see things we were missing before. The massive early galaxies were always part of the story. We just didn't know they were there because our tools weren't good enough to find them. There's a parallel here to the history of astronomy more broadly. Every major advance in telescope technology has revealed surprises. When Galileo first pointed a telescope at the sky, he found moons orbiting Jupiter, craters on the moon, countless stars in the Milky Way, all invisible to the naked eye but obviously real. When larger telescopes were built in the 1900s, they revealed that the fuzzy nebulae in the sky were actually distant galaxies, island universes far beyond our own. When radio telescopes were developed, they discovered entirely new types of objects: pulsars, quasars, the cosmic microwave background itself. Webb is continuing this tradition. It's a new kind of eye, seeing in wavelengths and at sensitivities that previous telescopes couldn't match. And as with every previous advance, it's showing us that the universe is more complex, more diverse, more surprising than we imagined. The massive early galaxies are just one part of this revelation. Webb is also finding the first brown dwarfs outside our galaxy, studying the atmospheres of exoplanets in unprecedented detail, revealing new features in the remnants of supernova explosions and much more. But perhaps most profoundly, Webb is reminding us that there's still so much we don't know. So many discoveries yet to be made. The early universe holds secrets that we're only beginning to uncover, and every answer we find seems to raise new questions, opening new avenues of investigation. Let that thought settle as we turn our attention to what these discoveries might mean, not just for cosmology, but for how we think about our place in this vast, ancient, and still mysterious universe. There's something profound about discovering that the universe was more mature at early times than we expected, something that compresses the timeline of cosmic evolution in ways that change how we think about our place in the story. Consider what it means for massive galaxies to exist just 300 to 500 million years after the Big Bang. In cosmic terms, that's extraordinarily quick. The universe goes from a hot, dense, nearly uniform state to containing structured galaxies with billions of stars in just 2% of its current lifetime. It's like a human being developing from a single cell into an adult in the span of a few months. The pace of evolution, the rapidity of structure formation, is remarkable. And this speed has implications for when and where life could have arisen in the universe. The conventional wisdom has been that life requires time, not just for galaxies and stars to form, but for enough generations of stars to live and die, enriching the interstellar medium with the heavy elements necessary for planets and organic chemistry. The first generation of stars, made only of hydrogen and helium, couldn't have had Earth-like planets orbiting them. You need carbon, oxygen, silicon, iron, all the elements forged in stellar cores and dispersed by supernova explosions. But if massive galaxies formed and evolved more quickly than we thought, if they went through multiple generations of star formation in their first few 100 million years, then perhaps the chemical enrichment of the universe happened faster too. Perhaps the conditions necessary for life, planets rich in heavy elements orbiting stable stars, arose earlier in cosmic history than we've been assuming. This doesn't mean life necessarily arose that early. There are other requirements beyond just chemistry: stable environments, liquid water or another suitable solvent, energy sources to drive chemical reactions, sufficient time for the complexity of life to emerge from non-living chemistry. All of these factors matter. But if heavy elements were abundant earlier than we thought, it opens the window for life potentially starting earlier in the universe's history. And this connects to a question that has fascinated humanity for as long as we've been able to ask it: are we alone? The abundance and timing of galaxy formation relates to this question because it affects the number of potential sites where life could arise. If massive galaxies, the kinds of systems that contain hundreds of billions of stars and presumably many times that number of planets, existed in larger numbers at early times, then there were more opportunities for life to begin, more rolls of the dice, so to speak. Of course, the existence of potentially habitable planets doesn't guarantee life arose on them. We still don't fully understand how life begins, what specific conditions are necessary, how probable the origin of life is given the right ingredients. Earth's life emerged relatively quickly in geological terms, appearing in the fossil record by at least 3.5 billion years ago, less than 1 billion years after Earth itself formed, and only a few 100 million years after the surface cooled enough for liquid water to exist. This suggests that life might arise readily when conditions are right, but we have only one example to work from, which makes it hard to know if Earth's story is typical or exceptional. What Webb's observations tell us is that the universe has been capable of hosting complex, mature galaxies for longer than we realized. If we think of galaxies as potential habitats for life, then the cosmic ecosystem has been rich and diverse for a larger fraction of the universe's history. And if life has arisen elsewhere, on worlds orbiting stars in those early galaxies, then the universe might have been inhabited by living things for longer than we've been estimating. There's something both humbling and comforting in this realization. Humbling because it makes our own emergence seem less special, less central to the cosmic story. If the universe was already full of mature galaxies when it was a small fraction of its current age, and if those galaxies potentially hosted life, then Earth and humanity are late arrivals, newcomers to a story that was already well underway. Comforting because it suggests we might not be alone, that the universe might be populated with life, perhaps even intelligence, distributed across space and time in ways we're only beginning to appreciate. Webb's discoveries also touch on something called the anthropic principle, the observation that the universe appears finely tuned for our existence. The fundamental constants of physics, Things like the strength of gravity, the mass of the electron, the speed of light, seem to have just the right values to allow for complex chemistry and stable stars and ultimately life. If gravity was slightly stronger, stars would burn out too quickly for life to evolve. If the strong nuclear force was slightly weaker, atomic nuclei wouldn't hold together, and chemistry as we know it would be impossible. If the cosmological constant, the energy density of dark energy, were much larger, the universe would have expanded too rapidly for galaxies to form at all. The fact that we exist to observe the universe means, by necessity, that the universe must have properties compatible with our existence. This is the weak anthropic principle, and it's not controversial. It's simply a selection effect. We couldn't observe a universe that didn't allow for observers. But there's a stronger version of the anthropic principle that suggests the universe is somehow designed or constrained to produce observers, that our existence provides insight into fundamental physics. Scientists generally prefer explanations that don't invoke anthropic reasoning if alternatives are available. But in cosmology, anthropic arguments sometimes creep in, particularly when discussing the values of fundamental constants or the initial conditions of the Big Bang. And Webb's observations of early massive galaxies touch on this discussion in interesting ways. If massive galaxies can form faster than our models predicted, it suggests that the universe is in some sense more efficient at creating complex structures than we thought. The path from the Big Bang to galaxies to stars to planets to life might be more straightforward, more robust, less contingent on finely tuned parameters than we've been assuming. This could be seen as reducing the need for anthropic explanations. If structure formation happens readily across a wide range of conditions, then perhaps our universe isn't so special after all. Alternatively, one could argue that the rapid formation of galaxies we're observing might itself be a consequence of anthropic selection. Perhaps in a multiverse of universes with different physical laws or initial conditions, only those universes where galaxies form rapidly enough to produce observers by 13.8 billion years are populated by beings asking these questions. In universes where galaxy formation is slower, observers might not arise until much later, or might not arise at all if other constraints intervene. These are deep philosophical waters, and scientists rightly approach them with caution. The danger of anthropic reasoning is that it can become a dead end, a way of explaining observations without actually explaining them, by invoking the mere fact of our existence. It's more fruitful to seek physical mechanisms, to understand why the universe has the properties it does based on fundamental laws rather than on the requirement that we must be here to observe it. But Webb's observations do suggest that the universe is, in a practical sense, good at making galaxies. The fact that large, complex galaxies appear so early, that the process of structure formation kicked into gear so quickly after the Big Bang, indicates that gravity and gas dynamics and star formation all work together in ways that efficiently produce the building blocks of cosmic structure. And this efficiency, whatever its ultimate explanation, is part of why we're here. If the universe were different, if galaxies took much longer to form, if the process were less efficient or more prone to failure, then planets like Earth might be rarer or might have formed much later in cosmic history. And if planets are rare or late, then opportunities for life are correspondingly reduced. So in some sense, the fact that we exist on a planet capable of supporting complex life might be related to the same factors that allow early massive galaxies to form. This doesn't resolve the anthropic question, but it adds another data point to our understanding of how special or typical our universe might be. And it reminds us that the story of the cosmos, the narrative arc from the Big Bang to the present, is intimately connected to our own story, to the existence of stars and planets and life. We are, in a very real sense, made of stardust, children of the universe studying itself. And the faster the universe can make stars and galaxies, the more opportunities there are for stories like ours to unfold. There's something strange about looking at galaxies from the cosmic dawn, something that bends our everyday intuition about time and existence. When we see light from a galaxy at redshift 13, we're seeing that galaxy as it was 13.5 billion years ago. The light left that galaxy when the universe was young, travelled through expanding space for most of the age of the universe, and is only now arriving at our telescopes. But what happened to that galaxy in the meantime? Where is it now? The answer is that we don't know, at least not directly. The galaxy we're seeing existed in the early universe, but by now, 13 billion years later, it has evolved, merged with other galaxies perhaps, grown larger, changed in countless ways. It might be part of a giant elliptical galaxy in the present-day universe, its stars aged and reddened, its youthful star formation long since quenched. Or it might have been torn apart in a violent merger, its stars scattered among multiple descendant systems. We can simulate these evolutionary pathways, use our models to predict what became of early galaxies, but we can't directly observe it. This is one of the strange features of cosmology. We see the universe at many different times depending on where we look, but each moment is frozen, unchanging. We can't follow an individual galaxy through its life because the light takes too long to reach us. The galaxy we see at high redshift and a galaxy we see nearby aren't the same system at different times. They're different systems that happen to exist at different cosmic epochs. And this connects to the question of what it means for something to exist. The light from that early galaxy is real, reaching us right now. But the galaxy itself, as it was when that light was emitted, doesn't exist anymore. It's been transformed by billions of years of evolution. In a sense, we're seeing ghosts, images of objects whose current states are forever hidden from us by the finite speed of light and the vast distances involved. This gives cosmology a certain poignancy. We can study the early universe in exquisite detail, see galaxies as they were in their youth, but we can never visit them, never see what they've become. The early universe is accessible to our telescopes, but forever in the past, unchangeable, already written. And the present state of those distant regions is hidden from us, their current light still en route, waiting to arrive billions of years in the future long after humanity has likely vanished. There's a philosophical question here about the nature of time and observation. In everyday life, we assume that things exist continuously, that objects persist through time even when we're not observing them. But in cosmology, observation and existence become entangled in strange ways. We can only see the past, never the present, of distant objects. And if the universe is infinite, there are regions so far away that we will never see them, even in principle, because their light hasn't had time to reach us, and never will due to accelerating expansion. Does it make sense to say those regions exist if we can never detect them? Or is existence something that requires, at least in principle, the possibility of observation? These questions touch on the philosophy of science, on what we mean by reality and knowledge and truth. And while they don't have definitive answers, they add depth to our appreciation of what it means to study the cosmos. When we look at Webb's images of early galaxies, we're not just seeing distant objects in space. We're seeing the past made present, moments from the universe's childhood brought forward through the medium of light to our current time. It's a form of time travel, not in the science fiction sense of moving our bodies through time, but in the real sense of information from one era reaching another. The photons that enter Webb's mirrors left their source galaxy when the universe was young, when Earth didn't exist, when the Milky Way was still assembling, and they've been travelling ever since, crossing an expanding universe, maintaining their quantum properties, until they finally encountered gold-coated glass and were focused into instruments that could decode their message. And the message they carry is profound. They tell us that the early universe was not empty and quiet. It was already bustling with activity, with galaxies forming and growing, stars igniting and dying, black holes consuming matter and powering brilliant quasars. The cosmic dawn was not a slow, gradual brightening, but a rapid awakening. And we're privileged to witness it through the light that has finally reached us after its long journey. For all that Webb has revealed, it's important to acknowledge what remains uncertain, what questions are still open, what we don't yet understand about these early massive galaxies. First, the measurements themselves are still being refined. Not all of Webb's massive galaxy candidates have been confirmed with detailed spectroscopy. Some might turn out to be closer than initially thought, their masses overestimated. The abundance of truly massive galaxies at cosmic dawn might be somewhat lower than the most provocative early estimates suggested. Follow-up observations are ongoing, and the numbers are likely to change as more data comes in. Second, even for confirmed cases, there are uncertainties in how we interpret the observations. The stellar masses we derive depend on assumptions about star formation histories, dust content, and the stellar initial mass function, which describes the distribution of star masses at birth. If the first stars were systematically more massive than stars today, as some theories suggest, then the light from early galaxies might require fewer total stars to produce, meaning the masses could be overestimated. Or if dust properties in early galaxies are different from what we assume, the corrections we apply might be wrong. Third, the theoretical side is complex and uncertain. The computer simulations that predict galaxy properties in the early universe depend on many parameters that aren't perfectly constrained by observation. The efficiency of star formation, the strength of supernova feedback, the properties of dark matter halos, the role of black holes, all of these have uncertainties. Small changes in these parameters can produce significant changes in the predicted abundance of massive galaxies. So the discrepancy between observation and theory might be reduced or even resolved as models are improved. And this connects to something fundamental about the scientific process. We're always working at the edge of what's known, in the zone where observations are challenging and interpretations are uncertain. This is where progress happens, but it's also where mistakes can be made, where initial conclusions might need revision. The history of cosmology includes several episodes where early observations of surprising phenomena were later explained by more mundane processes once better data was available or systematic errors were corrected. That doesn't mean we should dismiss Webb's findings as likely to be explained away. The multiple independent confirmations, the consistency across different surveys and instruments, the depth of follow-up analysis, all suggest that we're seeing something real. But it does mean we should hold our conclusions tentatively, recognizing that our understanding is still incomplete and will continue to evolve as more information becomes available. There are also deeper questions that we don't yet have answers to. What physical mechanism allowed some early galaxies to assemble so much mass so quickly? Was it unusual dark matter halo properties, efficient star formation, rapid gas accretion, or some combination? Why did some regions of the early universe produce massive galaxies while others didn't? What role did environment play, the local density of dark matter and gas? And what happened to these massive early galaxies? Did they grow into the most massive elliptical galaxies we see today, or did some of them lose mass through interactions and become something else? These questions will drive research for years to come. They'll require not just more observations from Webb and other telescopes, but also better theoretical models, more sophisticated simulations, and perhaps new insights into fundamental physics. It's possible that answering these questions will lead to discoveries beyond the immediate puzzle of early massive galaxies, new understanding of dark matter, star formation, black hole growth, or other aspects of cosmic evolution. What's exciting is that we're living in the time when these questions are being actively investigated, when the observations are fresh and the implications are still being worked out. Future generations will learn about early massive galaxies in textbooks as established facts, but we have the privilege of experiencing the discovery in real time, of watching the scientific community grapple with the implications and gradually build understanding. And perhaps most importantly, we should recognize that these discoveries, as significant as they are just one piece of a much larger puzzle. The universe is vast and ancient, full of phenomena we've barely begun to explore. Every answer we find reveals new questions, deeper mysteries waiting to be unraveled. The massive early galaxies are important, yes, but they're part of a story that extends from the Planck time, the earliest moment we can meaningfully discuss, to the far future when the last stars will fade and the universe approaches its ultimate fate. Before we move toward our closing thoughts, let's take a moment to appreciate the tools that made this discovery possible, the instruments and technologies that allow us to peer so far into space and time. The James Webb Space Telescope is a triumph of engineering, but it's also a triumph of international cooperation and sustained commitment. The project involved thousands of people from 14 countries, working over 3 decades to design, build, test, and launch the telescope. Engineers had to invent new technologies, actuators to position mirror segments with nanometer precision, a sunshield that could unfold reliably in space, cryocoolers to keep detectors at temperatures just a few degrees above absolute zero, infrared detectors more sensitive than anything previously flown. Scientists had to plan the mission in detail, what science questions to prioritize, what instruments to include, what orbits to use, how to protect the telescope from the sun's heat while keeping it powered and in communication with Earth. Program managers had to navigate budget pressures, technical setbacks, and political challenges. Astronomers had to wait, sometimes for their entire careers, hoping the telescope would work when it finally launched, and when Webb did launch. On December 25, 2021, aboard an Ariane 5 rocket from French Guiana, the collective breath-holding of the astronomical community was palpable. The deployment sequence was terrifying. 344 single points of failure, any one of which could have ended the mission. The sunshield unfolding, the secondary mirror deploying, the primary mirror segments unlatching and positioning, the cooling down to operational temperatures. Each step was carefully choreographed and executed by mechanisms that had never been tested in the actual space environment. When it all worked, when Webb reached its destination at L2 and began returning images, the relief and joy in the scientific community was overwhelming. Years of work, billions of dollars, countless sleepless nights, all vindicated by those first breathtakingly clear images. And now, 2.5 years into operations, Webb has exceeded expectations, performing even better than its designers hoped. But Webb doesn't work alone. Ground-based telescopes like the Atacama Large Millimeter Array in Chile or the Keck telescopes in Hawaii provide complementary observations. They can see different wavelengths, achieve different kinds of measurements, follow up on Webb's discoveries with their own capabilities. The Hubble Space Telescope, though older and less powerful than Webb in the infrared, continues to operate and provides valuable context and comparison. Future telescopes, like the Nancy Grace Roman Space Telescope launching soon, will add new capabilities, allowing us to survey larger areas of the sky and find even more distant galaxies for Webb to study in detail. And this connects to the broader infrastructure of modern astronomy, the supercomputers that process Webb's data, turning raw detector readings into calibrated images and spectra. The software pipelines developed by teams of astronomers and programmers to handle the data efficiently. The archives where observations are stored and made available to the broader community. The networks that allow astronomers around the world to collaborate, share data, and discuss results. It's all part of a collective endeavour that transcends individuals, institutions, and nations. Webb's discoveries belong to humanity, not to any one country or research group. The images are released publicly, available for anyone to see and appreciate. The data goes into archives that any qualified scientist can access and analyse. Papers are published in journals that aim for transparency and peer review. This open approach is one of the great strengths of modern science, allowing for independent verification and diverse perspectives. There's something beautiful in this, in the idea that people from different backgrounds and cultures can work together toward a common goal of understanding the universe. The political and economic tensions that divide nations fade into insignificance when we point our telescopes at the stars and share what we find. The early universe doesn't care about borders or ideologies. It simply is, waiting patiently for us to develop the tools and wisdom to comprehend it. And as we develop those tools, as our understanding deepens, we're not just gathering facts about distant galaxies. We're participating in something larger, something that connects us to every human who has ever looked up at the night sky and wondered what lies beyond. The ancient astronomers who tracked the planets with naked eyes, the medieval scholars who preserved and transmitted astronomical knowledge, the pioneers of telescopic astronomy in the Renaissance, the 20th century cosmologists who revealed the expanding universe, and now us, in the 21st century, with our space telescopes and supercomputers, all part of the same long conversation, the same quest to understand our cosmic home. Webb is just the latest and certainly not the last tool in this quest. But what a tool it is, allowing us to see further and more clearly than ever before, revealing surprises that will keep scientists busy for years to come, and reminding us that the universe is always more wonderful, more strange, more profound than our theories can fully capture. And that's something worth celebrating. As we enter the final portion of our journey together, let's reflect on what these discoveries mean for how we see ourselves and our place in the cosmos. There's a certain humility that comes from studying the early universe, from realizing that the cosmos was already ancient and complex when the first stars were being born, that galaxies were forming and evolving on timescales that dwarf human history, or even the entire span of life on Earth. When we look at a galaxy from cosmic dawn, we're seeing light that left its source when the universe was 300 million years old, travelling for over 13 billion years before reaching us. That galaxy has likely evolved into something unrecognisable by now, perhaps merging with others to form a massive elliptical, perhaps being torn apart, its stars redistributed among multiple descendants. And where are we in this story? We live in a galaxy that was just beginning to form when those early Webb galaxies were already mature. Our sun didn't exist yet, wouldn't exist for another 9 billion years. Earth wouldn't coalesce for nearly 10 billion years after those early galaxies shone. And human consciousness, the ability to build telescopes and wonder about the cosmos, emerged just a few million years ago. The last few seconds of cosmic time if you compress the universe's history into a single day. We're extraordinarily late to the party. The universe was already 13 billion years old when humans appeared, already full of galaxies and stars and likely, though we can't yet prove it, life. Most of cosmic history happened without us, without anyone to observe it or care about it. And most of the universe's future will also happen without us, long after the sun has burned out and Earth has either been consumed or frozen into a dead world, long after the last possible human descendant has vanished. And yet here we are, briefly, flickering into existence in this tiny corner of space and time, endowed somehow with consciousness and curiosity, able to peer back toward the beginning and forward toward the end, to comprehend, at least partially, the story we're embedded in. That's remarkable. That's miraculous, in a secular sense. The universe has brought forth, through processes we're still trying to understand, entities capable of studying the universe itself. We are the cosmos made conscious, matter contemplating its own existence and origin. This realization could be depressing, could make our lives seem insignificant against the vast backdrop of cosmic time and space, and sometimes it does feel that way. When you truly grasp the scale of the universe, the billions of galaxies each containing billions of stars, the unimaginable stretches of time before and after our brief moment of existence, it's hard not to feel small, unimportant, perhaps even pointless. But there's another way to see it, a perspective that transforms humility into wonder rather than despair. Yes, we're small. Yes, we're brief. But we're also part of something magnificent, something beautiful and intricate beyond measure. The atoms in our bodies were forged in stars, scattered by supernova explosions, gathered into new solar systems where planets could form and chemistry could grow complex enough for life. We are stardust, literally children of the universe, carrying within us the legacy of countless stellar generations. And we're here now, at this particular moment in cosmic history. Equipped through the accidents of evolution and the achievements of science with the ability to understand our origins, we can look back to the cosmic dawn and see galaxies being born. We can measure the expansion of space itself. We can calculate the age of the universe and predict its future. That's extraordinary. No other species on Earth can do this. Perhaps no other species in the galaxy can do this, though we don't know yet. So yes, let's be humble. Let's recognise that we're not the centre of the universe, not the point of creation, not the ultimate purpose of 13.8 billion years of cosmic evolution. But let's also marvel at the fact that we're here at all, that we can ask these questions and sometimes find answers, that we can build telescopes and decode the light from galaxies at the edge of time and space. One of the gifts of cosmology, of studying the universe on its larger scales and across its deepest history, is perspective, the ability to see human concerns in a broader context. When we contemplate the early universe, the sheer age and scale of the cosmos, our daily worries can seem less overwhelming. The argument you had yesterday, the deadline looming tomorrow, the political crisis dominating headlines, these things matter. Of course they do. They affect real people in real ways. But they're also temporary, local, small against the backdrop of cosmic history. Galaxies were forming and dying, stars were being born and exploding, supermassive black holes were consuming matter and powering quasars, all completely indifferent to human affairs because humans didn't exist yet and wouldn't for billions of years. This perspective doesn't invalidate human concerns. It doesn't mean we shouldn't care about our lives, our relationships, our societies. But it can provide comfort, a reminder that our problems, as real as they feel, are not eternal, not cosmic in scope. The universe will continue regardless of whether you finish that project on time or whether your favourite political candidate wins the election. And in some strange way, that's freeing. It allows us to take ourselves a bit less seriously, to recognise that we're part of something much larger, and that our brief time here is precious precisely because it's so temporary. There's a concept in philosophy called the overview effect, experienced by astronauts who see Earth from space, seeing our planet as a small blue marble against the blackness of space, beautiful and fragile, with no visible borders, no signs of the conflicts and divisions that loom so large from the ground. Astronauts often report that this view changes them, gives them a deeper appreciation for the planet and for humanity's shared fate, makes national and ethnic divisions seem arbitrary and petty. Studying cosmology can produce a similar effect, even without leaving Earth. When you understand that you're living on a planet orbiting an ordinary star in an ordinary galaxy, in a universe containing hundreds of billions of galaxies, when you realise that the atoms in your body came from stars that exploded before the sun was born, when you contemplate the vast stretches of time during which nothing like human civilization existed, and the equally vast stretches of future time when it will likely no longer exist, you gain a perspective that transcends everyday concerns, and this connects to something valuable about science more broadly. It's a way of thinking, a method for understanding the world that requires us to question our assumptions, to test our beliefs against evidence, to accept that we might be wrong, and to change our minds when the data demands it. The history of cosmology is full of discarded theories, ideas that seemed certain but turned out to be false. The static eternal universe of the early 20th century gave way to the expanding universe when Hubble measured galaxy redshifts. The steady-state theory, which held that the universe has always looked roughly the same, was abandoned when the cosmic microwave background was discovered, providing strong evidence for a hot, dense beginning. In our current era, we're seeing that our models of early galaxy formation, developed carefully over decades, don't quite match what Webb is showing us. And rather than clinging to those models, rather than dismissing the observations or attacking the scientist who made them, the cosmology community is working to understand what needs to change, What new physics or what refinements of known physics can account for the discrepancy? That's intellectual humility in action. That's what it looks like to truly follow the evidence wherever it leads. This kind of thinking, this willingness to update beliefs based on new information, is something the world could use more of. In our daily lives, in our politics and personal relationships, we often cling to our views even when evidence challenges them, because admitting we were wrong feels like weakness or failure. But in science, being wrong is simply part of the process. It's how we make progress. Every wrong idea identified and corrected brings us closer to truth. And if we can carry that attitude beyond science into how we engage with the world more broadly, we might find ourselves better equipped to handle the complexities and uncertainties of modern life. We might be less sure we're right about everything, but more confident in our ability to figure things out, to adapt when necessary, to learn from mistakes rather than deny them. There's something deeply satisfying about understanding how things work, about solving mysteries and finding answers. But there's also something beautiful about uncertainty, about knowing that we don't have all the answers yet, that the universe still holds secrets. The early massive galaxies discovered by Webb are a mystery, yes, but they're a productive mystery, one that's driving research, inspiring new observations and simulations, leading scientists to think more carefully about their assumptions and models. It's not a frustrating mystery like a crime with no clues. It's an inviting mystery, one that seems solvable with enough work and insight, that promises deeper understanding if we can just figure out the right questions to ask and the right ways to test possible answers. And in some ways, this state of uncertainty, this moment when we've discovered something surprising but haven't fully explained it yet, is one of the most exciting times in science. It's like reading a really good mystery novel. When you've gathered enough clues to know something significant is happening but haven't yet worked out the solution, the anticipation, the possibilities, the sense that revelation is just around the corner, all of that makes the journey worthwhile. If we already knew everything, if all the mysteries were solved and all the questions answered, science would be boring. It would be just rote application of known principles to new situations, useful perhaps, but not intellectually thrilling. The fact that nature can still surprise us, that our best theories can be challenged by new observations, that's what makes science alive and vital. That's what attracts people to scientific careers, the sense that there are still frontiers to explore, discoveries to be made, puzzles to solve. And this connects to a broader truth about knowledge and wisdom. Certainty is often an illusion. In everyday life, we act as if we know things with confidence, and mostly that works fine. But if we're honest with ourselves, much of what we quote 3 is provisional, based on incomplete information, subject to revision if we learn something new. The wise person recognizes this, holds their beliefs gently, remains open to being surprised or proven wrong. In cosmology, this attitude is essential. The universe is under no obligation to match our expectations. It existed long before we did, will continue long after we're gone, and its behaviour is determined by physical laws, not by our preferences or intuitions. The only way to learn about it is to observe carefully, to theorise tentatively, and to be willing to adjust our understanding when observations and theory don't align. This doesn't mean we should doubt everything all the time, that we should treat well-established science as no more reliable than wild speculation. Some things we really do know with great confidence. The universe is expanding, the Big Bang happened, the cosmic microwave background is real, general relativity accurately describes gravity under most conditions. These aren't just guesses or opinions, they're supported by overwhelming evidence and have survived decades of scrutiny. But even our most solid knowledge has boundaries, regions where it becomes uncertain, or where we know it must eventually be replaced by deeper theory. General relativity breaks down at singularities. Quantum mechanics doesn't tell us what happens during measurement. The standard model of particle physics doesn't include gravity. Every theory has its limits, and knowing those limits, Being honest about what we don't understand is as important as celebrating what we do understand. The early massive galaxies sit right at one of these boundaries, where our observations are pushing into regimes our theories weren't designed for, where the models make predictions that might not quite match reality. And that's okay. That's how science is supposed to work. We build models based on the data we have, use them to make predictions, test those predictions with new observations, and refine the models when necessary. It's an iterative process, a conversation between theory and experiment that gradually converges on truth without ever quite reaching absolute certainty. And perhaps that's as it should be. Perhaps a universe that revealed all its secrets easily, that matched our first guesses about how it works, would be less interesting, less worthy of study. The fact that the cosmos is subtle, that it requires patience and ingenuity to understand, that it can surprise even our most sophisticated theories, makes the endeavour of cosmology meaningful and profound. We live in a remarkable era for cosmology, perhaps the most remarkable there has ever been or will ever be. 100 years ago, we didn't know that galaxies beyond our own existed. We thought the Milky Way was the entire universe, with the spiral nebulae visible in telescopes being clouds of gas within it. It wasn't until the 1920s, when Edwin Hubble measured the distances to these nebulae using variable stars as distance indicators, that we realised they were separate island universes, galaxies in their own right, millions of light years away. The scale of the cosmos expanded enormously in that moment, a revelation that must have been simultaneously exciting and vertiginous. In the decades that followed, we learned the universe is expanding, inferred the Big Bang, detected the cosmic microwave background, discovered dark matter and dark energy, developed the standard model of cosmology. Each of these discoveries transformed our understanding, filling in the story of cosmic history from the first moments after the Big Bang to the present day. And now, with Webb, we're seeing the early universe with unprecedented clarity, catching the cosmos in the act of becoming what it is today, watching galaxies form and grow in real time, or at least in light time. This is a golden age of cosmological discovery, enabled by technology that previous generations could only dream of. Space telescopes, ground-based observatories with mirrors tens of meters across, gravitational wave detectors that can sense the ripples in space-time from merging black holes, neutrino detectors buried deep underground or frozen in Antarctic ice. All of these instruments are coming online and producing data, revealing aspects of the universe we've never seen before. But this golden age is also temporary. We live in a special time when the cosmic microwave background is still visible, when distant galaxies are still reachable by our telescopes, when the universe is old enough to have interesting structure, but young enough that we can still see back to its beginning. In the far future, billions of years from now, this won't be true. The accelerating expansion of the universe, driven by dark energy, will carry distant galaxies beyond our cosmic horizon, making them forever invisible. The cosmic microwave background will redshift into longer and longer wavelengths, eventually becoming undetectable. Future civilizations, if they exist, will have a much harder time reconstructing cosmic history than we do. And this connects to something called the anthropic principle in a temporal sense. We exist at a time when it's possible to learn about cosmic origins. Perhaps that's not a coincidence. Perhaps intelligence can only arise in universes and at cosmic epochs, where conditions are right for complex chemistry and stable environments, and those same conditions might be correlated with the ability to study cosmology. Or perhaps it's just luck, the fact that we happen to have evolved when we did, at a moment when the universe is revealing its secrets relatively easily. Either way, we should appreciate our good fortune. We live on a planet with a stable atmosphere and surface conditions, orbiting a star that provides steady energy, in a galaxy that's massive enough to contain heavy elements, but not so active as to be uninhabitable, at a time when technology has advanced to the point where we can build telescopes and detectors and computers sophisticated enough to study the cosmos. All of that is remarkable, improbable, precious. And we have, collectively as a species, chosen to use some of our resources to build and operate these instruments, to employ scientists and engineers to study the universe, to support research that has no immediate practical application, but that satisfies our curiosity about where we came from and where we're going. That choice, that investment in knowledge for its own sake, is one of the better things about humanity. It shows that we're not purely driven by survival and reproduction, that we have higher aspirations, that we care about understanding and truth. The massive galaxies Webb has found in the early universe won't cure disease or solve climate change or feed the hungry. They won't make anyone wealthy or powerful in any conventional sense, but they expand our knowledge, they satisfy our curiosity, they remind us that we're part of something larger and older and more magnificent than our everyday concerns. And that has value, real value, even if it can't be easily quantified in economic terms. Someday, perhaps in our lifetimes, we might find definitive evidence of life beyond Earth. We might detect biosignatures in the atmosphere of an exoplanet, or receive a signal from an intelligent civilization, or discover microbial life on Mars or in the oceans of Europa. And if that happens, it will be one of the most profound discoveries in human history, answering the ancient question of whether we're alone. But even if it doesn't happen, even if we remain alone as far as we can tell, the effort to find out is worthwhile, because it connects us to the cosmos, because it makes us think beyond our immediate surroundings, because it elevates us above the mundane. As we come toward the end of our journey together, let's return to where we began. The idea that every photon of light carries a story, and that galaxies, especially those from the early universe, have stories worth hearing. Each galaxy Webb observes is unique, with its own history of formation and evolution. Some formed early and vigorously, building up mass quickly through intense bursts of star formation. Others grew more slowly, gradually accumulating stars over hundreds of millions of years. Some merged with neighbours, their stars mixing together in great cosmic collisions. Others remained relatively isolated, evolving quietly in the voids between larger structures. Some hosted supermassive black holes that grew powerful and active, shaping their host galaxies through feedback. Others kept their black holes quiescent, allowing star formation to proceed unimpeded. And all of these stories are encoded in the light these galaxies emit, in the spectrum of wavelengths, the brightness and colour, the spatial distribution of stars. When astronomers study a distant galaxy, they're not just measuring abstract properties like mass and redshift. They're reconstructing a history, piecing together the narrative of that galaxy's life from the clues available in its light. It's like archaeology, but instead of digging in the ground for artifacts from past civilizations, we're collecting photons that have travelled across cosmic distances and analysing them for information about their sources. The massive early galaxies Webb has discovered have their own stories, stories we're only beginning to understand. How did they assemble their mass so quickly? Were they the products of unusually dense regions where dark matter collapsed early? Did they experience mergers with other proto-galaxies in the crowded early universe? What happened to their gas as star formation proceeded? Was it consumed entirely, turned into stars, or was some ejected by winds and supernovae? What happened to these galaxies over the billions of years since the light we're seeing left them? Are they now at the centres of massive galaxy clusters, or have they been torn apart and absorbed into other systems? We don't have complete answers to these questions yet, but we're working on them. Every additional observation adds detail to the story. Every new simulation explores possible evolutionary pathways. Gradually the narrative becomes clearer, the plot points connect. The character of each galaxy reveals itself through its light. And in telling these stories, in reconstructing the histories of individual galaxies and the population as a whole, we're also telling our own story, because we live in one of these galaxies. The Milky Way has its own history, its own story of formation and growth. It likely began as a small proto-galaxy in the early universe, not so different from the ones Webb is observing, though probably not among the most massive. Over billions of years, our galaxy grew, forming stars from collapsing gas clouds, surviving encounters and mergers with smaller galaxies, eventually developing the structured disk and spiral arms we see today. About 4.5 billion years ago, in one of the galaxy's spiral arms, a cloud of gas and dust collapsed to form our Sun and its planetary system. On one of those planets, the third from the Sun, conditions were right for life to emerge, and through billions of years of evolution, that life became complex enough to develop intelligence and technology and curiosity about the universe. And now, here we are, descendants of that first life, products of cosmic and biological evolution. Looking out at galaxies formed in the early universe and trying to understand how they came to be, knowing that their story is intimately connected to our own, that without the processes that formed those early galaxies, without the stars that lived and died and enriched the universe with heavy elements, without the particular history of galaxy formation and cosmic evolution that led to the Milky Way being the way it is, we wouldn't exist. So when you look at an image of an early galaxy from Webb, you're not just seeing a distant object of scientific interest, you're seeing a relative, a cousin in the cosmic family, a system that shares our origins in the Big Bang, that formed through the same processes that eventually produced our own galaxy and therefore us. And that connection, that sense of kinship with the cosmos, is part of what makes cosmology so compelling, so meaningful. The universe is not a cold, empty void dotted with isolated objects. It's a connected whole, a tapestry woven from matter and energy and time, with every part influencing every other part through gravity and light and the expansion of space itself. We're part of that tapestry, one thread among countless others, brief and delicate but real and present. And the light from distant galaxies travelling across billions of years to reach us is part of the connection, the means by which the universe communicates with itself, by which one part of the cosmos comes to know about another. And as we drift towards sleep, toward the end of this long exploration, let's hold on to that sense of connection, that awareness of being part of something vast and ancient and beautiful, something that began before we existed and will continue after we're gone, but that we have the privilege to know about and study and marvel at least for this brief moment we're here. Thank you for staying with me through this entire journey. Through 2.5 hours of exploration into one of the most profound mysteries uncovered by modern astronomy. We've travelled together across 13.5 billion years of cosmic time, from the present moment back to the cosmic dawn, to an era when the universe was barely 2% of its current age, when galaxies were just beginning to form and the first stars were illuminating the darkness. We began with the simple question of what James Webb saw when it looked toward the edge of time, and we found that the answer was both surprising and beautiful. Galaxies that shouldn't exist, at least not according to our models, massive and mature systems appearing in the early universe faster than we predicted was possible. We explored why these galaxies are so surprising, how they challenge our theories of galaxy formation, what they might tell us about the early universe and about our place within cosmic history, from the nature of light and redshift, through the technical achievement of Webb itself, from the cosmic dark age through the rapid formation of structure, from the role of dark matter to the mysteries of black holes, from the philosophical implications to the practical work of refining our models. We've covered enormous ground, touching on physics and astronomy, philosophy and human nature, the past and the future, the known and the unknown. The answer to our opening question, as honestly as I can give it, is this. James Webb saw that the universe is more dynamic, more efficient at creating structure, more surprising than we expected. It saw galaxies that formed fast and grew massive early, that challenge our models but also invite us to think more deeply, to refine our understanding, to appreciate that the cosmos still has secrets to reveal. And perhaps most importantly, it saw that we're living in a remarkable time, when technology and human curiosity have converged to let us witness the cosmic dawn, to see the universe's infancy with our own eyes, or at least with our instruments. These massive early galaxies don't overturn everything we know, but they do adjust our understanding, refine our models, remind us that nature is under no obligation to match our expectations, and that's okay. That's how science progresses, through this productive tension between observation and theory, each pushing the other toward deeper truth. If you enjoyed this slow drift through cosmic history, a like and subscribe really does help reach others who seek the same peaceful way to explore the universe. And if you have thoughts about these discoveries, questions about what they might mean, or suggestions for other cosmic mysteries you'd like to explore in this format, the comments are always open. To those who've been here before, who return to these journeys through space and time, thank you for your continued presence. You make this work meaningful. Wherever you are in the world right now, in whatever time zone, whatever season, whatever circumstances, I hope you're comfortable. I hope your breathing has slowed and steadied. I hope your thoughts have quieted, or at least become gentler, less urgent. I hope your body feels heavy and warm, ready for rest. You've given me more than 2 hours of your attention, and I'm grateful for that gift of time. Look up at the stars if you can, or imagine them if you can't. Those points of light, some nearby and some unimaginably far, all part of the same cosmic story we've been exploring. Among them, too distant to see with your eyes but visible to telescopes like Webb, are galaxies from the cosmic dawn, their light travelling for over 13 billion years to reach this moment, to reach you. All those photons carrying their stories across space and time, finally arriving at consciousness, at a mind capable of understanding what they represent and where they came from. You are stardust that has learned to wonder about stars. You are the universe studying itself. And in this moment, as you drift towards sleep, you carry with you the knowledge of cosmic dawn, of impossible galaxies and mysterious origins, of a universe vast and ancient and beautiful beyond measure. That knowledge doesn't solve your problems or change your circumstances, but it offers perspective, a reminder that you're part of something larger, something magnificent, something that inspires awe and humility and gratitude. Dream, if you dream, of distant galaxies, of stars being born from clouds of gas and dust, of light travelling across expanding space, of cosmic time measured not in years but in billions of years, of a universe full of mystery and wonder. Dream of questions yet to be answered, of discoveries yet to be made, of future telescopes that will see even further and reveal even more. Dream of the long story of cosmic evolution, from the Big Bang to the present day to the far future, when the last stars fade and the universe grows dark and cold, and dream of our brief moment within that story, our chance to look around and ask why and how and what it all means. Sleep well. Rest in the knowledge that the universe is both stranger and more beautiful than we imagined, and that every answer we find opens new questions, new mysteries, new invitations to wonder. Thank you for exploring with me. Thank you for your curiosity and your attention. Thank you for being here. Good night. Dream of the cosmic dawn. Dream of impossible galaxies. Dream of light from the edge of time, and wake tomorrow with a sense of your connection to it all, to the stars and galaxies and the vast sweep of cosmic history. Good night.